Okay, here we go. First, let's talk a warm up on stuff we've already done. Related rates part one the other day. We're going to go a little further today, and related rates will get a little harder, so let's make sure you're on the right track. Look at this problem on the homework number 2 on the fun sheet. It's like we did the other day. So the process is to, first of all, write the givens they tell you in calculus terms. For example, they tell you when a cube is contracting at a rate of 5 cubic centimeters per hour, they're giving you that volume is changing with time, which is dv dt in calculus. Contracting means it's decreasing, so dv dt is negative 5 cubic centimeters per hour. Use the units as a guide as to what you're being told. If it's cubic centimeters, that's what tells me volume. They didn't say, they won't necessarily always say the volume is this. They use the units as a guide. Then identify what they want. They want how fast the edge is changing. Now, if a cube has all edges the same, then we could say the volume of the cube is x cubed. So I would say they want dx dt when volume is 10. We'll deal with that in a second, that instant. X, though, is changing at different rates at different times. They will always tell you in a related rates problem when they want you to find the rate of change. After you've got the given and what you want or when, you go to the equation. We have an equation already, volume is x cubed. You differentiate with respect to time, which is to say we take the derivative d dt of both sides. The left side is dv dt, the right side is 3x squared dx dt. Last is you substitute in and solve. Sometimes the substituting will require a little bit of work on your part. For example, you know dv dt, that's not an issue, but you don't know x. So you're going to have sometimes a little pre-algebra or algebra or pre-calculus to do to solve for what you need to put in. If the volume, I'm going to take a little side note here. If the volume is x cubed and at the instant they wanted it's 10, that would imply that the x at the instant is the cube root of 10. Now that I know x at the instant, I can go back and calculate dx dt is dv dt, which is negative 5, divided by 3x squared, or 3 cube roots of 10 squared. I can calculate that and attach the appropriate units. X is obviously going to be decreasing. If the volume is decreasing, the edge is decreasing. Whatever your decimal answer is. And the units, because x is a length, the units of x length changing over time would be centimeters per hour. Right? That's what we did the other day. I also want to remind you of set 47, which is the fundamental theorem of calculus, or how to find area under a curve using calculus. We used to use, or we still will use infinite rectangles once in a while, but there's an easier way we talked about in set 47. Review set 47's notes if you're not cool. Let's do A as a warm-up. Now, in every case, I actually gave you an example here. In every case, I'm giving you a summation that's meant to be illustrating how to find area under a curve by infinite rectangles. Your goal is to figure out what is the curve, what's the region, and then find that area a different way. Instead of using the formulas and the limit, we're going to express this by what's called a definite integral, which involves taking an antiderivative and evaluating it at the upper limit minus the lower limit. In this case, I looked at this, and the first thing my eye went to is this. The region starts at 1. That inside value in the function is the starting value. That's where that starting value of the definite integral, that lower limit of the integrand, tells you where the region starts. Then I need to know where the region ends. Now, this 3 here tells me the total width is 3. if the total width is 3 and I started at 1, that implies the region ends at 4. That's how I got the upper limit. After that, I'm trying to extract what the function is. Now remember, the function, or this integrand, is the sum of many delta x's. That's the 3 over n. That doesn't help me anymore. I'm done with that. F at, and you've got some, typically, what the x is at which you're drawing the heights comes from the starting point plus so many delta x's over. So if I look at the inside and see some kind of crazy sum with an I in it, that's probably the x, and whatever that is inside is the function. Now in this case, 1 plus 3 over ni is inside, so that feels like the x. That means that which it's in is the function. Everything else that's there is 5 root x. That's where that came from. All right, so once you've written it as an integral, then the idea is you anti-differentiate it. I'm going to use the power rule, and to use the power rule, it helps to write the root as a power. If I rewrite the square root of x as x to the 1/2, then I use the power rule. The 5 just stays out front, and the power I raise by 1 and divide by the new power. That's where I'm getting x to the 3/2 divided by 3/2. Cleaned up, 5 over 3/2 is 10/3. That's where that's coming from. All right. Now the second part of the fundamental theorem then is you take your antiderivative, which is x to the 3/2, and put in the upper limit and subtract what you get when you put in the lower limit. So if x to the 3/2 evaluated at 4, that's where 4 to the 3/2 comes from. Subtract 1 to the 3/2. 4 to the 3/2 is square root 4, which is 2, then cube it, which is 8. 1 to the 3/2 is easy enough, that's 1. 10/3 then times 7 is 70/3. That's where I'm getting my answer. All right? That's the expectation for A, B, and C. Write it as a definite integral, then integrate and evaluate. Now, moving on to the new stuff. Related rates can be harder when there's more variation, more variables in the problem, instead of just 2 variables if there are 3, for example. So look at this example in the notes. Related rates part 2, 3 variables and indirect relationships. Say you had a funnel and liquid was draining out the bottom, at a hole in the bottom, at a rate of 2 cubic inches per second. The height of the liquid then obviously will drop, and the radius and the height will decrease with time. How fast is the liquid falling, or how much is the height changing when the liquid is 7 inches high, right? So first thing, draw, we got that done for us, and identify the variables. In this case, the radius, the height, and the volume are all going to vary. We had that in our picture. Second, what we are given and what we want and when. Now, if liquid's draining out at 2 cubic inches per second, that's a volume. We're given dV dt is negative 2 cubic inches per second. Volume is decreasing with time, which means volume's derivative is negative. Use the units again as your guide to decide why is that volume. Now, what they want is how fast the liquid is falling. Now, that's not a radius measure, that's more of a height measure. So they want dH dt when h is 7 inches. All right, so far, pretty much normal. Now, the appropriate equation in this case is just a geometry equation. The equation for volume is 1/3 pi, or pi over 3 r squared times the height, 1/3 pi r squared h. Now that's the first part of the hard part. You have 3 variables there, and that makes the calculus substantially harder. Now there's 2 ways to deal with this. That's why I have a part A and a part B. We'll deal with it both ways, and you'll see that one of the ways is usually a little easier than the other, and we'll go that way most times. The first is before you do your calculus, you actually try and substitute to get an equation that's easier to work with. Then your calculus is easier. The other relationship is not always obvious, and it's not always the same. These problems differ from one to the other. You're going to look for some other relationship besides the volume. Now this one's not, like I said, not obvious, but if you were to slice this and cross-section it, the relationship of the radius to the height of the water would always be the same as the relationship of the radius to the height of the cone itself, because the fluid conforms to the shape of the cone. If I were to then show the dimensions of the cone itself, it would be like a 6 by 10 right triangle. By similar triangles, then I can get another RH relationship. R is to 6 as H is to 10. Proportionality between the sides. Then my question is, all right, well, which one should I solve for, R or H? Well, given that I want dH dt, it seems like I want H to stay in the equation, which means I don't want R. So I'm going to call R 6/10 H, or 3H over 5 when I reduce, right? Okay, so if I put that into the equation, pi over 3, and instead of R goes 3H over 5, which all needs to be squared because the radius is squared. Cleaned up then, I'm looking at pi over 3 times 9H squared over 25 times H. Take the 3 out, and I get 3 pi over 25 H cubed for a volume equation. Now that is easy to work with for the calculus. I could take the derivative with respect to time. dV dt is 9 pi over 25 H squared dH dt. Be careful with your derivative. Obviously, you've got to get that right. And let's substitute in. I know dV dt is negative 2. 9 pi 25 H squared. They say at the instant we're looking at, the height is 7. So I'm going to put in a 7 there. dH dt then is what I have to solve for. If I do that, dH dt is negative 50 over 9 pi times 7 squared. And the units then would be inches per second. Height change with time. It's a rate of change, so it has time units in it too. And if you want to, you can calculate that. And negative makes sense because the height is decreasing. And that's one way to do it. To substitute to get it down to two variables before the calculus. The other option, and you better be good with your calculus, is to do the calculus with three variables, then substitute after the calculus. So if you were to say volume is pi over 3 r squared h, you could take the derivative with respect to time of the three variables. If you do, I beg you, use product rule, otherwise you're toast. Now that's why it makes this a little more dangerous. dV dt is pi over 3. The derivative of the inside by product rule would be first stays the same, r squared, times the derivative of the second, that's dH dt, plus second stays the same, h, times the derivative of the first, 2r dr dt. Now at that point, I see what I want in there. It's kind of buried, but it's right there, dH dt. And I have a lot of stuff to substitute in for. That's going to involve the similar triangles. dV dt, you know, it's easy enough. You can put negative 2 in there, and pi over 3 is cool. But the r and the dr dt, not so obvious and not given. I know the h is 7, 2 is 2, but I still need the r and dr dt before I can actually finish and solve for dH dt. So I still have two things I need to find. Well, any way you look at it, you're going to have to use that similar triangle relationship, and this time you're just going to use it later. Now, by that same idea, r is 3/5 of h. You can get both facts. When h is 7, r is 21 over 5. If I put 7 in for h, I get that r is 21 over 5. Likewise, if I were to differentiate this equation with respect to time, dr dt is 3/5 dH dt. That can go in for dr dt, 3/5 dH dt. Now, you have this is a mess, but you have a common factor of dH dt. So you can pull a dH dt out. I guess the best way to go is to clean up this big mess and go something like this is 441 over 25. I'm going to pull the dH dt outside plus, my goodness, let's see, 441, 882 rather, over 25. I hope that's right. I know that 7 times 3 is 21. 21 squared is 441 times 2 is 882 over 25. So all said then, I'm looking at negative 2 is pi over 3. Let's see, 3 to 13, 1,323 over 25, dH dt. So dH dt is, let's see what we got here, negative 2 times 3 times 25 over 1,323 pi. And am I feeling that's the same? Negative 50 up top, and if I dumped 3, I believe you would be looking at the same answer, 441, so I believe these are correct. All right, and the inches per second, they are the same if you put them in your calculator. All right, so that's the idea. Now I think you can agree that the first way was easier. The product rule leads to a lot of mistakes, and so I'd suggest you substitute before you do your calculus when you have 3 variables. Look for another relationship and substitute first. Another possibility is when you have an indirect relationship. For example, if Isabel pours salt onto the table at a rate of pi over 3 cubic centimeters per second, that's a volume change. They ask about how surface area is changing or lateral surface area is changing. Those two don't relate to each other. So in such a case, I try and shoot for an in-between measure, like the radius or the height. And if I could use dV dt to inform me about how the radius or the height is changing, then I could use that in a second problem to find out how the lateral surface area is changing. Kind of like a unit multiplier problem where you have an in-between measure. If I had, for example, inches and I wanted to go to miles, I'd first go to an in-between measure of feet. The same kind of principle here. We're going to an in-between relationship. So we're given here that dV dt is pi over 3. It's positive because salt is pouring in, but volume is changing in a positive way. Cubic meters, centimeters per second. We want dA dt, and that's the lateral surface area actually, at time equal 8. That's kind of weird, time equal 8. I'm going to have to work with that later, I'm sure. All right, so let's start with the volume. I know that volume is pi over 3 r squared h. And just as we talked about, if we can find another relationship, then we should do that before we go. Now here's the other relationship. In this case, the radius equals the height. So I'm going to go pi over 3 r cubed. I could have also put in for h and got h cubed. Either way, I think it's going to be fine. dV dt is pi over 3 times 3r squared dr dt. Therefore, dr dt is that dV dt, which is pi over 3, pi over 3 times 1 over pi when I divide this over, and divided by the radius squared, which I don't actually know. That's a problem. So as usual, there's sometimes going to have to be some finding before you proceed on here. They tell you at the instant that they ask that time equals 8. So what does that mean? Well, I assume it started with no salt. If the volume is coming in at pi over 3 cubic centimeters per second, then at time equal 8, is pi over 3 cubic centimeters per second times 8 seconds, or 8 pi over 3 cubic centimeters per second. Now, if the volume then is always pi over 3 r cubed, that implies then that the instant they talk about, the radius is 2. If I throw that in there, and I get dr dt is 1/12, and that's centimeters per second. All right. Now let's talk about how that will help us in the surface area. If we consider the lateral surface area, that's the side of the pile, not the bottom circle that's sitting on the table. So this lateral surface area, which is LSA, but I'm going to call it A, is pi r L, where L is the slant height. Now that, again, is two variables. Man, this problem's got variables all over the place. So let's talk about that. Now I know that R is R and H is there, but it's the same as R. It says the height is equal to the radius. So by Pythagorean theorem, R squared plus R squared is L squared. So 2R squared is L squared. So L is root 2 R. If I use that in the area equation, then I get pi r times root 2 r, or the surface area is pi root 2 r squared. Now that's pretty easy for calculus, and now we're home free. dA dt is pi root 2 times 2r dr dt. You know that at the instant, the radius is 2, dr dt is 1/12, so it feels like the surface area is root 2 over 3 pi, changing at a rate of, not is, sorry, changing at a rate of root 2 over 3 pi centimeters squared per second, area over time. All right. That then required an in-between relationship. You'll have one like that on the homework. Hopefully that'll get you started. There was a replacement on the homework last night. Here are the answers to set 47, I believe. This is set 47. Or is it set 46? I can't remember. But we're a little behind on questions. We'll get caught up gradually. There's the answers to that problem. That should be it. Have a good day.